Hi, this is chapter 14, Censuses, Surveys, Polls, and Statistics. This is going to be a little bit of an introduction to statistics. So it's really, really good because for two reasons. There's a lot of statistics and numbers that are being thrown out there and that we're reading in our newspapers and stuff like that. So just seeing a little bit of where they're getting these numbers and the process that they go through to get those numbers really gives you more of an understanding of those numbers. And to be honest, you're going to see how those numbers could be very off and could be misleading. So sometimes, we're going to see all the errors that could be possibly made when statistics is being done. That's one reason why I'm really happy that we are going over this chapter 14, but also is it's it's a great introduction to statistics so that if you were to take that in the future, you'd be all that more prepared. So in 14.1, we're introduced to this enumeration problems. Enumeration problems are just counting problems. We just want to count how many items there are in a particular. It might be, I want to count the number of hats I own or whatever, like if any question that it starts with how many, that's an enumeration problem. So we could be counting for an example, we could be counting these quarters that are in this jar. Now, actually, these types of problems are actually really important, and some really important ones are for for our environment. It's important for us to kind of know how many tigers there are left in this world, for so that we can protect them if they are endangered. So there is purpose for this type of mathematics, and Florence Nightingale used this type of mathematics statistics to help her discover that doctors should wash their hands before they go from one patient to the next. So she was simply counting the number of deaths that occurred when doctors did not, wash their hands, and the number of deaths that occurred in the hospital when they did wash their hands. So sometimes just counting things is a very important thing that can really bring to light a lot of important information to us. So that's why counting is important. The US government wants to count. They do it every 10 years. They do a census of all the people living in the country. And it's very important to them because they need to know how many people are living in Fresno County. It's important because that determines how much money and funds that we're going to be receiving for our schools, for our roads, for our things around our area. So then it's very important to the government to know how many people there are living in the United States. And that's a enumeration problem where we have to get together and we have to count. Literally, a census, and that's one of our first definitions here. A census is where you do your best, and I mean, to line up everybody in the population of interest. So if it's the United States, you are doing your best to count the number of people living in the United States, and you're going to do it by walking down, having someone walk down every block of every, neighborhood in the entire, United States, and numbering how many people live in that house, how many people live in that house. And a lot of times they get other information as well, like what's your income, I don't know, what your nationalities are, or whatever. They also like to, while they're at it, they get more information for their information, whatever. So that's a census. When you try to take everybody in a population, line them up, and literally just count them, starting from the first person to the last person. And that's what it would that and it's one way of trying to obtain the number of people in a population of interest for you. So that's our first definition here, is a target population, is the set of items being counted or we're trying to make a conclusion about. So it's like this jar of quarters that I show a picture here. We want to ask how many quarters are in that jar. And the first way to attack that question is to do a census of the quarters, which means to literally, pour out that jar and line up those quarters and count every single quarter in that jar. That is what a census is, to do a head count. And it's a really, really hard and involved process. And you can look in our textbook, but they say it costs billions of dollars to try to count the people in the United States. When you're talking about really large populations and trying to line them all up, kind of, and count them, like, you're not literally going to line them up, but like they're going to line them up in some way, the people in this neighborhood, the number of houses, or whatever. They're going to try to count them in an ordered manner. But sometimes we're going to, so this is the first method of attack. We can literally line up the objects and do a head count to the best of our ability. The larger the population, the harder that task is going to be. And sometimes we're going to see that task is like nearly impossible. Even for the census takers in the United States, like we have some people that are homeless, that are, that aren't connected to a house, that are roaming around, that are moving around. That, and then if you think about it, we have people dying daily, and then there's new births being born. So like the number of people who live in the United States is changing too. So it's just a very difficult number to actually obtain. But the actual number, and you'd probably have to say, of people alive at this moment, at this very second, that is called the parameter, the exact count of the population. And they say a parameter might be the number of people in the population, or it might be just the number of a characteristic of people in the population, but it's the exact count. If I would have lined them up and counted every head, that's the number I would get, the parameter. This is often a number in statistics that it's not logistically feasible to actually get that number. And that leads us to the next idea of, if I can't pour out this jar, if I don't have time to pour out this jar and line up every quarter, what's the next best way to kind of make a best estimate for the number of quarters in this jar? And that's often what we resort to, just because of time and money that we have, right? So the second method would be to kind of maybe take with your finger and like measure like an inch, what an inch is in the jar, and then just like, so let me write that. And then just measure how many quarters are in like the top inch of the jar. And that's called, I'm taking a sample. I'm taking a subset. A subset is a smaller group within the whole set. So like this is the whole jar, of oh darn. Okay, so if I just took like, maybe I measured like the best of my ability, like at the top inch here of, as you can see, hopefully you can see what I'm talking about. It's this top inch of quarters. And if I took those out and counted just that top inch, and then let's say, that's 20 quarters, then what I could do is I could measure, well, how many inches similar are in that jar. And then if I think, oh, it looks like there's 3 inches in that jar, then maybe I'll just do 3 times 20, and that would give me kind of an estimate of how many quarters are in there. So just taking the top inch of quarters, that's called a sample, because you're taking some of the total quarters in the jar. So that's what sample is, a subgroup, a smaller subgroup of the population used to draw conclusions of the entire. And that's what I did there is I used what was in the sample to give me an estimate of how many were in the total sample. So I thought, okay, well, there's 20 here, 20 quarters here. I counted them. And then, so maybe there's 20 quarters there, there's 20 quarters there. So there's a total of, I would add them all up, of 60 quarters. That's how that would give me like a rough estimate of the number of quarters in that jar. So that first part is that first top inch of quarters that I used to that is called the sample, and they're part. It's a small group of the larger part of all the quarters. And the process of using a sample to make a conclusion about the entire population is called survey. It's a survey. Sampling is the act of choosing a sample, and we'll kind of really get into that more in the next section. And that's something very important. If we don't pick a sample that's a very good sample, then our whole estimate is not going to be very good. So sampling is a chapter to itself. So that is the process of picking a sample. How do you go about that? And then a sample, a statistic is an estimate about the population using the sample. So when I came up with, I think that the total number of jars in there is 60, that was because I came up with that number because of the information in my sample. So they call that number a statistic. So whenever they're talking about in the newspapers and they say, oh, well, statistics say 50% of people get divorced, they did not actually count all the people in whatever maybe if they're talking about divorce in the United States, they didn't count everybody in the United States. They did not count the number who divorced in the United States. What they did is they looked at a small sample, maybe just people in Fresno County, and they said, well, how many, and they counted all the divorcees in Fresno County. And they used that information to maybe talk about the whole country, so that would be a bad sample to use is Fresno County, but that's an example so when a statistic is an estimate, it's not the exact number. The parameter above was the exact number. The statistic is your estimate. In our case, I estimated there was 60 quarters in that jar. And we call that our N value. Your textbook calls it the N value, your alleged count of all the individuals in the population. In this case, 60 is our N value, what we believe to be the number of quarters in that jar. And our target population is the set of items that you're interested in counting. So in this situation, it was our quarters. So if you just to review and summarize so far, there's 2 ways to count things. You can pour it, focusing on just this jar of quarters, you can pour out the jar of quarters. So on top here, And you can line them up and count you. It might take a few hours to do that, but you can do that. And you will find the exact number called the parameter of quarters. And maybe if, let's say I did do that and I found out that there's exactly 64 quarters. Okay. The shortcut, like lazy way of doing it would be to just count a small portion of quarters and use that to estimate the total amount of quarters. We call that a survey. The method of coming about with answering that enumeration question is we did it using a survey method, which is a method that uses a sample to help us find the total estimate of the quarters. So those are the two types. You can either spend forever counting the quarters. That's what's called a census. Or you can take a small sample and use that sample to estimate the total number of quarters, and that's called a survey. Okay. Moving on to the next thing. A sampling error is the difference between the parameter, if I would have counted all those quarters, poured them all out, counted every single one, and the statistic. So in my problem, I said, if I had poured them out, I would have found out there's 64 of them. And if I would have estimated using my sample, I would have counted 60 of them. And the difference between those two is 64 minus 60. So that's your sampling error. Okay. And that's because I used a sample to estimate the actual number. So our sampling error, guess, would be 4 there. Okay. So we're going to see two different types of math types of problems that we're going to see come from this section. And the first is called a one sample type of problem. And sometimes we're not interested in like the number of individuals. Maybe we're interested, like I mentioned before, the number of divorced people in the United States, the number of people with a particular characteristic of interest. So in this problem, we're interested in the number, we're not interested in all the candies as we were all the quarters in the previous problem. We're interested in the orange candies. We want to estimate how many orange candies there are. So they say, how many orange candies in the jar of 225 candies are there in that jar? Okay, your sample, so what we did is this is called a one sample because we take a sample only one time. Your sample of candy of 10 candies has 3 oranges. So can you tell me how many, or estimate for me, how many oranges are going to be in the entire candy jar? So we must have taken out 10, maybe we closed our eyes, we picked out 10, probably the ones on the top. And we found 3 of them to be orange. And then we asked ourselves, well, how many oranges are in the entire jar? So the idea behind solving this problem is the idea that the proportion of oranges that are in the sample, we believe that the proportion of oranges, a proportion is the fraction of oranges in the sample is going to be equal to the fraction of oranges in the entire jar. So let's put this in. The proportion in the sample will be the same as the proportion in the entire jar. So that means what we can do is we can say that the number of oranges in my sample over the total in my sample is equal to, so this is the proportion of oranges in the sample, 3 over 10. Because there was 3 oranges and a total of 10 that I sampled. So that proportion is equal to the number of oranges that are in the jar, which is our unknown n value, the number that we're trying to find, over the total number of candies in the jar, which is 225. So the number of oranges to the total number of total number of candies in the total number of oranges in the jar over the total number of candies in the jar is equal to the total number of oranges in the sample over the total in the sample. So there is our math equation that we can use to solve this problem and to give us an estimate of the oranges in the jar. So this is just a little reminder, and this is not going to be like super complicated. You just have to memorize these few steps and it won't be too hard. But whenever you have one fraction equal to another like this, then we can cross multiply. It's a shortcut of the algebra that needs to be done to solve this problem. And then we get 3 times 225. Just move this up a tiny bit. 3 times 225 is equal to 10 times n. Then, when we have an algebraic equation like this, where you have a number times by a letter is equal to another number, what we can do is we can simplify this side. 3 times 225, we can pop that into our calculator and find that that is 675. So 675 is equal to 10n. And then whenever I have a number times a letter on one side, so it's like this number is known as a coefficient. And I describe it as like there is a number here, n, attached to the back of this coefficient, then 10. When we see this is equal to a number, then we always just have to have this step memorized that we are going to end up dividing by the coefficient that is the number in front of the letter on both sides of the equation. And the reason for this is because I'm taking this n and I'm multiplying it by 10, and I need to do the opposite to undo that. So the opposite of multiplying n by 10 is dividing n by 10. So I divide by 10 on both sides. And actually, let me rewrite this equation. I'm just going to rewrite everything that I have here. And I'm going to divide by 10 because that was my next step. So you can clearly see all the steps. You can see the prior step of me just writing out the equation, 675 is equal to 10 in, and then now you see the next step that I divided by 10 on both sides. Then 675 divided by 10 is 76.5 is equal to Rn. Now, of course, there's not 67.5 candies in there. So we would just round that. And 67.5 rounded is 68. So we would say, to the best of our knowledge, there is 68 orange candies in the jar. And that's how we solve this problem. And that is a one sample problem that we will see in this section. All right, one sample, I would call it one sample sampling problem. And here's the equation for it. This is kind of what we did. The number of oranges that was in our sample was, we're going to call K. And then the number in our sample, we're going to see that this is consistent to future statistics classes, that always the number in your sample is lowercase n. Then the number of oranges, the number that you're trying to find really here, is the capital N is equal to, and P is the number of total candies in the jar. So I expelled out everything for you, but the number of oranges in the sample over the total number in your sample is equal to the number of oranges in the entire jar over the total number of candies in the entire jar. So let me just emphasize here, K is the number of oranges in the sample. And N is the number in our sample, and it's the number of oranges and all color candies, right? So that is the first problem, is the one sample sampling problem, right? And then we have one more problem in 4.1 to notice another method, this is another survey method that another way that we can use a sample to help us find the answer to an enumeration problem is a two-sample estimation. Okay, we're moving on to a two-sample estimation. This is where we use two samples to help us measure or count something. So this is the capture-recapture method, also known, and it's a method for estimating the size of a population using two samples. Here's an example. There's 500 fish captured from a small pond. All of those people, all of the ones, this is called your first sample. These 500 fish, all of them are tagged. And then they are released back into the pond. A few days later, 120 fish are caught. And they make note that 30 of those 120 happen to have tags on them. And they want us to estimate the number of fish in the pond. So the idea behind this type of problem is that the proportion of tagged fish or tagged individuals in the entire population, so that fraction of tagged fish to the entire population, or fraction of the tagged fish in the entire population, will be the same as the fraction of tagged fish in the sample. So this is how they're going to write it. They're going to say, oh, well, that means from the first sample, this 500 of the N amount of fish were tagged. That represents the fraction of fish that were tagged. 500 fish were tagged of the total number of fish in this pond. And that fraction is going to be equal to the number of the fish that were tagged over the total in our sample. This is the total number of fish. Well, this is the number of fish that were tagged in our sample over the total number in our sample, right? 30 over 120. And then we're going to go through the same exact steps to solving this. So we're going to cross multiply, and that's going to equal 500 times 120 is equal to 30 times n. Then I'm going to do with any simplification or mathematics that I can do on either side of the equation right now. I'm going to go ahead and do. So I can do 500 times 120. That is 60,000. Then we can divide by, then like I said, the next step will be dividing by the coefficient. I'm going to rewrite this so you can see it as a separate step. And then I get n, and I pop in my calculator, 60,000 divided by 30, and that is 2,000. So the estimated total number of fish in that pond is 2,000. And that is just amazing to me, that all we had to do was take two samples, and now we have a really good estimate for the total number of fish in that pond. I mean, that is way better than actually trying to literally line up all those fish that are in that pond, depending on how big it is, that would be extremely time consuming, and that would be really hard to like count those, like, I mean, what would you do? Take it out when you count? Okay, there's one, like take it out, and then like two, and then three, and then like, well, you probably have to drain the pond, to like make sure you got every single one, and you'd probably have to kill them because they would have to take them out of the water. I don't know. Like it would be just a terrible process. And when you want to know like bigger questions, like how many blue whales are left in the entire world, you can't drain the whole ocean, obviously, like you and you can't line up all those whales and do a head count, like, so methods like this of taking, in this case, two samples and using it to give us a good educated guess of the actual number of fish in the pond they're just, I'm so glad we have these methods, right? Because they're so helpful. So here I wrote down at the bottom for you, like, the equation, and I'm saying these are approximately equal, and this is an estimate of the number of fish in the pond, right? That is 2,000. But this is K over N2, and N sub 2 is the total number in your second sample that is tagged and not tagged. And then N1 is the total number in your first sample. Remember, your first sample everyone got tagged. So all of those will be tagged in your N1. And then capital N is the total number of fish in the pond. That's the number you're after. And then K is the number tagged in the second sample that you caught. Because in that second sample, some are going to be tagged, some are not. So I wrote out everything here for you just to make sure that, and then you can just figure out these numbers and plug them in the places that you need to plug them in. And hopefully that'll make it a little easier for you to set up and solve problems like that. And that concludes 14.1. I'm excited to introduce 14.2 to you, and we're going to go into, like I said, we're going to go into sampling and methods of sampling to help us make sure that our estimates are as accurate as possible. All right, bye class.